Hello, it's Mr. Lopriato here. So I am making a video on drawing Lewis structures. All right, so we've seen this in class, but this should serve as good review and a little bit of practice. So hopefully, at whatever point you're coming to this video, by the end of watching it, you're like, okay, I can do these. I feel good. All right, so just reviewing the steps. There's 5 steps. It's a little wordy, but step one, we count up all the valence electrons. We know the number of valence electrons of each element based on its position in the periodic table, right? So think about the group number. If it's group 14, it's 4 valence electrons. If it's group 17, it's 7 valence electrons. So being able to identify where the element is on the periodic table is so important, which is why when I'm doing all my work, I have my periodic table handy. All right, so you should be in the habit of having that. All right. Step two, you're going to choose a central atom. All right. Usually the first element in the formula, usually only one atom of the element is in the formula. And usually it has the lowest electronegativity, although those first 2 tips are going to help us more. Step three, we're going to connect all the outer atoms to the central atom with single bonds. Step four, we're going to give all atoms, with the exception of hydrogen, an octet. All right, we're just going to add lone pairs. Typically, those outer atoms are going to need 3 lone pairs, and we'll see what's going on with our central atom. All right, and then in step 5, you're going to recount your electrons. All right, now each bond is going to count as 2 electrons, and the lone pairs will count up. If your count from step 1 matches step 5, you are good. All right, and hopefully that'll happen. If you have too many electrons in your drawing, we can use that double bond trick. That trick will reduce the total count of electrons by 2 by removing 2 lone pairs from 2 adjacent atoms and instead putting in a double bond. And we can do that multiple times if need be. And if we don't have enough electrons in our count at step 5, we would be adding the extra electrons as lone pairs to the central atom. That would be an expanded octet. All right, so we're going to do 5 examples that just kind of reinforce these steps. So CH3Cl. All right, well, step 1, we got to add up the valence electrons. All right, so carbon is in group 14. It has 4 valence electrons. Hydrogen in group 1 has 1 valence electron, but it's 1 valence electron per atom, and there are 3 atoms of hydrogen. So we're going to have to multiply it. All right. And chlorine, 1 atom of chlorine gives us 7 valence electrons. It's in group 17. So when we add this up, we are going to get a count of 14. All right. We got to pick a central atom. Carbon is first in the formula. There's only 1 atom of it. So I feel good with carbon. All right. Step 3 is to connect all the other elements with single bonds. It doesn't matter where, like the order, right? So I'm going to do 3 hydrogens and I'm going to do a chlorine. It would have been fine if the chlorine was on top or on bottom or on the side. That doesn't matter. That is step 3. Step 4 is to give all elements an octet. Now, hydrogen doesn't need the octet. Hydrogen follows the duet rule. Chlorine, an outer element, is going to need 3 lone pairs. And if we check the carbon atom in the middle, since each bond counts as 2 electrons towards the carbon atom, carbon has an octet already. So we're good to go there. So that was step 4. And now step 5, we got to recount our electrons. All right. So on the chlorine, I see 6 valence electrons as 3 lone pairs. And each bond counts as 2. So 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, our counts from step 1 and 5 match each other. So this is the Lewis structure. We should feel confident in that. Booyah. All right. How about SiO2? Okay, our second example. Well, step 1, we count up the valence electrons. Silicon is in group 14. It is right underneath carbon. It also has 4 valence electrons. Oxygen is group 16, so it has 6, but that is 6 valence electrons per oxygen atom, and there are 2 oxygen atoms, so we're going to be multiplying it by 2. So when we do 6 times 2, that is 12 plus 4, we have a total of 16 valence electrons. All right, we got to pick our central atom, Si. It is the first element in the formula. There is only 1 atom of it. All right, so we should feel good with that. All right, we're going to connect 2 oxygens. right? That is step 3. Step 4, we're going to give lone pairs to give each element an octet. There's no hydrogen here, so nothing's following the duet rule. All right, so I draw in those double bonds. Now, the silicon atom in the center has currently 4 valence electrons from the 2 bonds. So we're going to give it 2 lone pairs. That gets it to 6 valence electrons. And here now we are at 8. That is our octet. All right, so that is step 4. Step 5. All right, let's do the recount. So 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 valence electrons in step 5. So we have too many. We have 4 too many. So what we're going to do, we're going to do that double bond trick, right? So we could take the lone pair on the silicon atom and a lone pair on the oxygen. They are adjacent, right? They touch each other. We can remove them. And in their place, we would put a double bond, right? So that reduces the count by 2 electrons. But we're still not good with step 1. So we can actually do it a second time. I'm going to do it with the other atom now, the other oxygen. So again, I'm removing a lone pair from each, and then I get to go back and put in a double bond. That reduces it again. So now the counts match. So the Si still has an octet, right? It has 8 valence electrons around it, but now they're all in the form of bonding electrons. Silicon doesn't have any lone pairs, and the outer oxygens each have only 2 lone pairs now. Okay, so SO4 2-. This is a polyatomic ion. So when we do step 1, right, sulfur is a group 16 element, so that's going to be 6 valence electrons. Oxygen is also group 16, so 6, but we're going to be multiplying that by 4 because there's 4 atoms of oxygen, and there are 6 valence electrons per each oxygen atom. But now, because it is a 2- charge, we are going to add 2. Right? This tells us that this molecule has gained 2 electrons, and they are somewhere throughout the molecule. So when we add it up, 6 plus 6 times 4 plus 2, that gets us to a total of 32 electrons. We're going to pick our central atom. We should feel comfortable with sulfur. It's the first atom in the formula, and there's only 1 atom of it. All right, so step 3, we're going to draw the sulfur. We're going to draw the oxygens, right? We're going to connect them all. Step 4, we're going to give each oxygen a set of lone pairs to give each oxygen atom an octet. Now, while I'm doing that, I will point out the central sulfur atom has 4 bonds connecting to it, right? The 4 separate oxygen atoms. So that is 8 valence electrons. That is an octet. All right, and now step 5, we're going to recount. So if I start on the left side, 1, 2, 3, 4, 5, 6 valence electrons from the lone pairs, 7, 8 for the single bond. Each oxygen has 8, right? So 8 more electrons here, so that's going to be 16, 8 more 24, 8 more 32. All right, so we do have 32 electrons in this count. So this is the structure. We can feel good about it. All right. Again, we count up all of the dots, and each bond counts as 2. So we have 24 dots and 8 electrons in the 4 single bonds. All right. XeF2. So you might be thinking, Mr. Lopriano, xenon, noble gas. They're not supposed to bond. They're not supposed to, but fluorine, as the most electronegative element, can make these things happen. All right, so when we go to count our total numbers of electrons, xenon contributes 8 valence electrons, and each fluorine atom contributes 7, and there are 2 atoms of fluorine. So 8 plus 7 times 2, that gives us 22. All right, we got to pick a central atom. All right, we can go with xenon. Only 1 atom of it. It's first in the formula. All right, and is much lower electronegativity than fluorine. All right, so we draw it out. Step 3 is to connect the outer atoms. So it's going to be 2 fluorines. Step 4, we got to give everyone an octet. So the fluorine gets 3 lone pairs, right? Each of them. And the central xenon atom needs 2 lone pairs, all right, because it has only 4 valence electrons around it in the form of those bonds. All right, step 5. Let's count up our valence electrons. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so when we count it up, we have 20. We don't have enough. All right, so this is the expanded octet. We have 2 valence electrons left over. What are we going to do? We're just going to stick them on the central atom. This would be an expanded octet. All right, now we have 22. And my last example in this video, we've seen a number of different scenarios. Here, we have a simple compound, H2O2. This is hydrogen peroxide. This is from all of the chemistry jokes where, the chemist walks into a bar, but we don't really have a central atom. All right, so if we go for the count, hydrogen has 1 valence electron. We'll multiply that by 2 because there's 2 atoms of hydrogen. Oxygen, group 16, has 6 valence electrons. We will also multiply it by 2 because there's 2 atoms of oxygen. So that gives us 14 valence electrons. Well, here's the trick. We don't quite have a central atom, but we know that hydrogen can only form 1 bond. So oxygen is going to have to be more in the middle. So what we're actually going to end up doing, we'll connect an oxygen to another oxygen, and we'll connect a hydrogen on both sides. All right, so we can get structures like this. We will have situations. You might have tried to have put an oxygen up top, but you will find that you will get kind of a funky system here. All right, so it just takes a little bit of chem intuition. All right, but sometimes when we get bigger structures, they can be kind of in lines like this. Step 4, we add the octets. So we give each oxygen 2 lone pairs. And in step 5, we would double check our count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. So just want to show you kind of a unique scenario where we get more of like a linear looking structure that can also occur. All right. So we've seen the steps, right? It's all 5 steps. You follow them. Be flexible. Step 1 is based on the periodic table. Step 2, if you were to do step 2 wrong, you can retry it. And then remember, we have those different tips for if the recount doesn't match in step 5. We've seen a few examples here. All right. So hopefully this helps us understand how to draw a Lewis structure. All right. And we feel confident in doing these questions on our own at this point.